introduction. Well, so as we already know, we have these DSLs, domain-specific languages, that are used by the community to solve problems in specific domains. And like any programming language, these DSLs need to be tested. So we use test suites. We create test suites to test programming languages, and also we can use test suites to test DSLs. And mutation testing is a common technique used to improve such test suites quality. So what is mutation testing? Well, mutation testing is a software testing approach that uses that introduces small syntax variations, small syntax changes into the sources, and generates mutated versions of the programs, like these programs with a small syntax variation. So by using these varied versions of the programs, we can apply the test suite to these mutants, and we generate, we divide this set into the mutants that have been detected by the test suites that are called kill mutants, and those that are not detected by the test suites that are called alive mutants. By measuring the number of mutants that are killed by the test suite, we obtain a metric that is called the mutation score, and it's a metric of the quality of the test suite. We can, as you can see, we can include new test cases in the test suite to be able to kill more mutants, and well, this process is iterated until we reach the total, the 100% score of the kill mutants. Okay, so well, this is a brief example of the mutation testing process for an automata. Well, this automata is accepting the binary numbers. So we have this test suite that we have an input of the number 0 and an input of the number 1. So the number 0 is accepted, is even, and the number 1 is not accepted by the automata, is odd. So by applying a small syntax variation, as you can see, we modify the transition, the symbol of a transition, and in this case, the number 0 is also accepted by the mutant, by the mutated version of the automata, and number 1 is also accepted by this mutant model. So in this case, the test suite hasn't detected the mutant, so the mutant is alive. And if we add cleverly a new test case for the number 2, this one, then in this case, the mutated version, the mutant model, doesn't accept this number 2. So in this case, the mutant is killed, and our test suite has been improved, and the process has been enhanced, as we can see. So the mutant is killed in this case. So, well, by doing this, you know, we can create a mutation testing tool for each domain, but this is costly, and also is usually is encoded by hand, that is error prone, and incurs in high cost of maintenance. So to alleviate such inconveniences, we have created this model-based engineering solution to generate mutation testing tools specific for each domain, but in an agnostic way. So we have called this proposal, this framework, Wodel-Test. Well, to introduce Wodel-Test a little bit, it's a model-based solution to engineer mutation testing tools. It is divided in two main roles: the mutation testing tool creator, that provides like the specification of each mutation testing tool that is going to be generated, like the language support, the domain meta model, the model to text transformations, and the text to model transformations if they are needed, the mutation support, that are the mutation operators coded in Wodel, and an equivalence criteria to detect those equivalent mutants that must be discarded in the results. And also the execution support, that is how to compile the programs and how to execute the tests. By using these ingredients provided by the mutation testing tool creator, the Wodel-Test framework generates a mutation testing tool ready to be used by the tester that only needs to provide the program under test and the test cases, the common ingredients for any mutation testing tool. And after that, this mutation testing tool generates a report with the results. We have already created mutation testing tools for automata, logic circuits, the Java language, ATL, chatbots, that is where we are going to talk today, and so on. So how do we have created this mutation testing tool for chatbots? Well, we have used this intent-based chatbot meta model created by Sara Perez Soler and collaborators that are members of my research group. And, well, to introduce what is a task-oriented chatbot, briefly, these are chatbots that are specific for solving a specific task, like booking a ticket, ordering a pizza, setting a medical appointment, and so on. They are used via text or speech recognition, and we have many frameworks or approaches that uses allow to generate this kind of chatbots like Dialogflow, Rasa, and so on. Well, just to point out that we are not covering in this work this ChatGPT or this kind of open domain chatbots that are can interact with the user on any topic. And well, this is left for future work. This is not the target of this presentation. So how do we chatbots work? Well, the user inputs a natural language phrase, and then, as we know, the chatbot provides a response. Well, feel free to interrupt me if you have any question. And, well, how does it work internally? Well, what the chatbot does is to match the natural language phrase that is the input of the user with like some categories that are called intents, and after that it operates internally with the parameters, and it may call some external service like a REST API or a database. And finally, the chatbot provides a response that may ask for more information to the user or may solve the issue. So how is the natural language phrase as an input matched with the intent? Well, with the category, as we are saying. Well, what we call these input phrases from the users are utterances, okay? So these are examples of utterances made by the user. Hi there, I need to fly from Madrid to Seville on Thursday at 8 a.m. Goodbye. Okay, these are examples of possible natural language phrases from the user. So the chatbot tries to match this message with an intention. This is what we call the intents. And how does it work? Well, we provide like training phrases, okay? We provide training phrases. We include training phrases within the chatbot to train the model, the natural language processing model, with like examples of phrases with a similar meaning, and we categorize them with this intent name element, okay? So, for example, I need to fly from Madrid to Seville on Thursday at 8 a.m. The intent would be booking a flight. So these are examples of natural language phrases used as training phrases within the chatbot for greetings. So hi there, hello, hi, hey, they are greet intentions. Airplane ticket from Madrid to Barcelona tomorrow at 10 a.m. Flight from Madrid to Bilbao on the 19th of October 2024 at 11:30. They are intents. They are intentions of booking a flight. So, well, just not to. Well, this is another example, and we need to know that there are also parameters within the natural language phrases, and they are extracted from the phrase and input as parameters within the chatbot. So we have the origin of the flight, the destiny of the flight, and like the time when it does take place. So these are called entities, okay? So it's kind of the name we give to these parameters. And after that, the chatbot provides the response that can be created in text or as an image. And also, it can consult, it can access external API REST or databases and so on to create the response to the user that may ask for new information, for extra information, or provide the solution to the task. How do we test chatbots? Well, we usually create test cases based in the input and the output of the interaction. Okay, so we create these test cases, but we need to test complex conversations. So these are conversation flows that can be with many branches, as you can see. So we have used Botium and Rasa test, okay, in this work. And this is an example of a Botium test. So we have single test interaction that there are only the input phrase and the output phrase, and also combinations of multiple tests that we use like a template. In Botium tests, we use templates, and they are substituted by the natural language phrases corresponding to each, the utterance and the response from the chatbot. So this is how we test these conversation flows with many bifurcations, okay? They can be extended like a tree. So how do we apply this mutation testing for chatbots? Well, what we have done, this is an illustration of what we have done, is, for example, we have a scenario where we are in a restaurant and we can order a coffee or order wine, and we have these training phrases for each kind of drink. So the user inputs like, tell me what kinds of coffee I can drink here. Okay, so imagine that we apply a mutation operator that keeps the two most different phrases. So to apply these mutation operators, we have included the semantic similarity of the phrases. And this is an example, okay? So the two most different phrases in this case are the ones with the lowest semantic similarity. So we keep these ones. We remove the ones in red, and these are the remaining ones for ordering a coffee. So now we can see that, well, the chatbot may get confused, okay, because there are only two training phrases for ordering a coffee, and these two training phrases are the same from ordering wine. So imagine that the test case, the test suite for this input phrase matches, the chatbot matches the ordering wine, is confused, is the wrong intent, and the test or test suite doesn't detect that is a wrong behavior. We are missing this test case, okay? So the test suite needs to be improved. So then we detect, if we add this extra case, this extra test case, we detect that it is a wrong behavior, and the test suite is working now, and we have fixed that. Okay, well, to go ahead, we have created mutation operators for training phrases, for intents, for entities, for actions, and for conversation flows. And all these operators emulate common errors made by chatbot developers, okay? So this is how our approach works. We parse the input chatbots into the model we have used, and we annotate with the semantic similarity. We mutate using the Wodel DSL the annotated versions of the chatbots, and after that we generate like the back implementation of the mutated versions of the chatbots. And we apply the test cases, the test suites, to these mutated versions of the chatbots, and we collect the results. Okay? So our work revealed that we performed an evaluation, and our work revealed that almost all the mutation operators that we designed revealed some room for improving the test suites in the chatbot set that we used. And also, well, there was room to improve the test suites for the three kinds of test suites that we used. And, well, the mutation testing process was also performed in a reasonable time lapse, okay? In less than 90 minutes for almost the 70% of the 15 chatbots set. So to conclude, Wodel-Test is the engineering of mutation testing tools for DSLs. Wodel-Test may be a better option when we need to access the source code of the mutants, reason which mutants reduce the mutation score and why, and to test new mutation operators. We have this DSL for mutation operators that is called Wodel, and we can easily add new mutation operators to the framework. As a future work, we would like to automate the detection of semantically equivalent mutants in the case of chatbots, well, by using confidence decrease heuristics. Also, we would like to automate the synthesis of tests able to kill the aligned mutants. We would like to include some optimizations to the mutation testing process because it is still time consuming, like parallelizing the mutant generations. And we would like to adapt, finally, we would like to adapt our approach to LLM-based agents. Okay, so, well, thank you. Thank you very much. I'm not sure if I can play a short video of the tool working, if you like. If you prefer to ask me some questions, is your both. Okay, so maybe I can play the video. Is silent, so I can play the video and you can see it working. And ask me questions about it. Well, I think it's not very... Oh, sorry. Well, sorry. Well, it's like the project we are using in is not very... Sorry. We are using an Eclipse-based solution, and this is like the test, the RASA test, sorry. Well, we can select the mutation operators here to apply from the whole set of mutation operators. And well, this is like generating the mutants of the chatbots, of the chatbot models. Well, I think it's enough here. So as you can see, it's, well, it's only, that was only the mutant generation part. Now it's launching the, like all the infrastructure to interact with each mutated version of the chatbots. So they are launching these are 4 mutants in this execution, and these are the RASA server for each of the mutants. So they are executed in a different port. They are executed locally, okay, but in a different port. Well, I'm not sure. This is, I think this is starting with the RASA test. That is not, it's only a RASA execution. It's not Botium. Well, maybe I can go forward. Sorry. This is the Botium execution. So these are like the tests failing and do you have any question? Yes. Sorry.
Thank you, Pablo. First of all, we are going to
Thank you.
If you have any question, you have time for 1 or 2.
Yes.
Thanks for the nice talk. You mentioned at the start the original problem statement was that mutation testing is too specific to each kind of programming language or something like this, right? And then the goal was to make it more generic with the Wodel model. My question is, at the end, when you describe the mutation testing for this chatbot, for example, the delete operators, and you were defining these operators, they look very specific to the scenario.
Yes.
So, how would this generalize, especially if you talk about, for example, your goal of generalizing LLMs, right? There you won't have intents, and they are. Oh, sorry. You got the question, right? So maybe you can use that example to say how you would generalize this, right?
Operators we use.
More. So. Yeah, exactly. So.
Yes. Well, as you can, if the domains are very different, the operators would be different too, but we use like the common syntax for the DSL. Skin, I think for Sorry, I have well, I'm not going to open the Eclipse instance, but I have here like some set of, this is the set of operators that we used. Well, it's not very intuitive, I guess, okay? These are like deleting a training phrase with the max, with the highest similarity. So this is the operator specific. This is specific for this chatbot metamodel. The task of
Language itself, so I don't know what this language is where you're defining these operators. Is it something that I can use for my DSL?
yes, for sure. It's like domain open. It's agnostic. So we include here the meta model, and this language, the syntax is common. The syntax, the grammar is common for any meta model, but the operators, the implementation is specific for this meta model.
So it has understood. So essentially, the two inputs are the meta model and the operators, and then it's going to generate tests for that meta model.
That's right.
Okay. Sure.
Any more questions? Thank you.